Okay, YouTube, this is my second video in a brief module on solving exponential equations, and in our last video we had solved expressions such as this one here. We say 2 to the unknown power is equal to 7. What would this unknown power have to be? And what I know is it's somewhere between 2 and 3. The only reason I say that is because 2 to the second power is equal to 4, and 2 to the third power is equal to 8, and 7 is an output between 4 and 8. So this is some number between 2 and 3, but the idea is that I want to solve for this exactly. So in our last video what we did was we borrowed from a property that we called the one-to-one property to solve exponential equations. And basically what I suggested was we'll first isolate the base, which we see the base of this unknown variable expression is actually isolated. There's nothing around it on this side. But we'll try to rewrite both sides as having the same base. So in other words, I would like to say that 2 to the what power is equal to 2 to the what power here, where I'm going to be able to fill in some number here that would give me 7. The unfortunate thing, though, is this. We say 7 is not a natural power of 2. That is, I can't take 2 to the power of some whole number that I know off the top of my head and get 7 for an output. So what we're going to have to do is we're going to have to adopt a modified method here. So I'm going to make a suggestion here is isolate the base. When you're solving exponential equations, you isolate the base. So we have some isolated base here on the left. And then we say step number 2 is this. I'm just going to write this. We're going to say 1 to 1 property. And I'm going to write a question mark. Can I use the one-to-one property like I tried to do here? And in this case, I cannot. So what we're going to do is this. We're going to use the inverse. Let me rewrite this here. Inverse property of logarithms. Okay, and I'm going to list that inverse property of logarithms here, and it essentially says this. If you had some base to the x power equal to some constant here, what we would do is we would take the log base b of everything on the left, of b to the x. And we would also do log base b of everything on the right, which is this c right here. And what's going to happen is we have log base b of b to the x. You notice that you're taking an exponential expression and you're taking the log of that. So when you take the log of an exponential expression and their bases match, what happens is these two things right here, log base b and b to the x, they wipe each other out and you just get x. And the nice thing about this is on the right side we're going to get this value right here, which is something we can evaluate. As a matter of fact, what I'm also going to do is use the change of base formula. And remember that change of base formula says that if you wanted to rewrite log base b of c, you could rewrite it as common log of c, which is this thing right here, over the common log of b, which is your smaller listed number, your subscript number. But these would be the same thing. But the idea here is that we can undo an exponential expression using its inverse, which is a logarithmic expression. So I'm going to show everybody how this looks when you have something like 2 to the x equals 7. But essentially, now that I have this base isolated and I've determined that I can't use the one-to-one property, what I'm going to do is I'm going to take the log of both sides. I'm going to take the log of this exponential thing. And the thing that I want to really point out here is this, that their bases have to match. So what I'm going to do is I'm going to take the log base 2 of everything on both sides. What you do to one side of an equation, we're going to do to the other side. On the left side, I have 2 to the x. On the right side, I have 7. So what I end up with here is this now. I say the log base 2 and the 2 cancel out, and I get left with x. And x is equal to log base 2 of 7. So this, using our change of base formula, would be the same thing as if we took the log of 7 divided by the log of 2. And so now what this allows us to do finally is evaluate this expression for a value that would give us approximately 2 to the power that would give us 7. So what I'm going to do is I'm going to take the log of 7 first. So we say 7. And I'm actually going to have to use, let's see, I have a common log right there. So common log of 7 divided by, and I'll put in parentheses 2, the common log of that, divide that. We get about 2.807. And I think that 3 decimal places are approximately good here. I'm going to box this here. So we think this is the solution. So the idea is that I'd want to check it. So I get 2 to the, blank equals 7. We're claiming that this is 2.807. And if on the calculator here we take, let's do this, we say 2, and it'd be to the power of, I think it's this key here, 2.807. Check it out. You get approximately 7. We don't get exactly 7, but the only reason why is because we rounded our answer here. So I want to do this again here over here on the right and say, well, how would I solve an exponential equation such as this? Well, now you notice, first things first, the variable expression, its base is this 10. So what we're going to want to do is we're going to isolate this base if at all possible. So that means I'm going to start by subtracting 4 from both sides. And we end up with this. We get 10 to the 2x minus 3 power is equal to 21 minus 4, which is 17. So now that we have this base isolated, what we're going to do is we're going to take the log of both sides, and you'll notice that the base is 10, so I'm using a log base 10. I do want to point this out. I don't have to write that 10 there. Remember that if you don't write a base on a log, we assume that it is a base of 10. I got to quit getting ahead of myself. So this is 17 on the right. On the left side, we have 10 to the power of 2x minus 3. And the idea here is that our log base 10 and our 10 to the power of, since they're logarithmic and exponential, they're inverse functions and undo one another. So what we get left with on the left side is just 2x minus 3. And on the right side, this is actually equal to, and I'll try to keep this clean here, we say log base 10 of 17. So to finish this off, this is just now an algebraic equation. You've now got your x down on the ground level here. So we could say if I add 3 to both sides, then I end up with this new expression that says 2 times whatever x is equal to log base 10 of 17 plus 3 onto that, and then we're going to divide everything here by 2. So the idea here is that our equation has one solution, and it is this solution right here. And we can find this on a calculator, and that's what we want to basically be doing. So I'm going to start by evaluating the top, and I say, well, 17, I want the common log of that, so here's our 1.2304-ish. We're going to add 3 equals, we're going to divide by 2 equals, so we get about x is about 2.115. So x 2.115 is our x value, and I do want to check this. So if I said 10 to the 2 times 2.115 minus 3 power, all of that, plus 4, do I get 21? And the nice thing about checking this is you actually see that you're just undoing everything we just did. So now if I divided by 2 last year, if I took 2.115 times 2, I'll just take, 2.115, I'll even round it, times 2, we'll subtract off 3, so there's our 1.2-ish, 3-ish back. We're going to take 10 to the power of this. So I just did that, and I added 4 onto that. And I get about 20.982, which is about 21, which is the output we were seeking here. So if you cannot, you can isolate the base and use the one-to-one property if possible. But if you can't use the one-to-one property, we'll just use a log on both sides to undo the exponential equation. Cheers.